Hello everyone, today we are excited to present our project titled Viscosity of Bitumen at different temperature using Newton divided differences. We, which is from group C, will show you how numerical methods help us to understand bitumen behavior. That's something important in pavement engineering. Let's get started. Before we jump into the technical details, let's introduce our amazing team. We have got Lau Tai Wei, Nurul Dianah binti Ruhaizat, Zaid bin Harun, Aisyah Humaira binti Muhammad Alawi, which is me, and Muhammad Adha bin Shamsul Kamar. Each of us contribute to this project, and we are proud to present it together. So why is this topic important? Well, numerical methods are like secret tools for pavement engineers. They help us predict how bitumen, the sticky stuff that hold road together, behave at different temperature without running endless lab tests. Road face scorching heat in summer and freezing cold in winter. If we understand how bitumen viscosity change, we can design road that won't crack or melt easily. That's where Newton divided difference come. It's a clever way to estimate values like viscosity at temperature we didn't directly test. For the birds, we save time and money by reducing lab work by pick the perfect bitumen for any climate and build roads that last longer and handle weather like camps. In short, this method helps us create stronger and smarter roads.
Hello, my name is Nurul Dianah binti Ruhaizat, so I will present about the objective. So for the objective, firstly is to create a problem using temperature and viscosity data of bitumen. Second, to evaluate Newton's divided difference as a suitable numerical method. And lastly, to solve the problem and estimate viscosity at 55 degrees Celsius using a chosen method. For the literature review, in pavement engineering, bitumen is a key material used to bind asphalt. Its viscosity thickness changes with temperature affecting how it performs during construction and under traffic. Accurate viscosity values are needed to design roads that last and perform well. For the challenge, viscosity is usually measured at a few temperatures only, but we often need to know it at temperatures in between like 55 degrees Celsius. The solution is this study used Newton divided difference method to create a formula interpolating polynomial from known data, estimate viscosity at 55 degrees Celsius, which was directly measured, show how this helps improve pavement design in different weather conditions. Okay, this is our methodology. So in this project, it aims to estimate the missing bitumen viscosity at 55 degrees Celsius using Newton divided difference method. This numerical technique is ideal for creating and interpolating polynomial from unevenly spaced data points, allowing accurate estimation of value between known temperatures. The result will help assess bitumen performance under different climate conditions for better pavement design. So this is our flowchart. Now I will pass it to Adha.
Hello and Assalamualaikum. So this is my part. My name is Muhammad Adha bin Shamsul Kamar. My metric number CF252010021. So for the first, I will explain about filler table. F for facts, I for ideas, L for learning issue, and A for action plan. So for the first facts, the viscosity of bitumen changes with temperature, and the ideas we get use Newton divided difference to find an interpolation polynomial. For the learning issue, what is Newton divided difference method? How is it applied to tabular data? And then the action plan, review Newton's divided difference formula, tabulate the divided difference from the given data, construct the polynomial. And then next, viscosity values at various temperature are available in tabular form. And then the ideas use the polymer to estimate viscosity at an unmeasured temperature, 55 Celsius. And then the learning issue, how to substitute a value into an interpolation polynomial, how accurate is the estimation, and the action plan. Evaluate the polynomial at 55 degree. Validate if possible using Esknon curve or experimental point. And lastly, bitumen's performance in pavement is highly dependent on its viscosity, and the ideas growing viscosity at various terms help in material selection and performance prediction. And then the learning issue, why intermediate temperature behavior important in pavement design, how does it affect cracking and rutting. And the action plan, uh, we discuss practical relevance of viscosity estimation, refer to standard superwave, and explain how viscosity affect design decision. Thank you.
Okay, next is the calculation. From the problem statement, the problem that occurs is about a civil engineering wants to know the viscosity of bitumen at 55 degrees Celsius. Measuring it can help engineering assess how the bitumen will resist flow and maintain shape on a hot day. So the data on the table below, we got the temperature for the 40 degree, 50 degree, 60 degree, and 70 degree Celsius. For the 40 degree Celsius, we got 1600, the viscosity. For the 50, we got 880, 60, 570, the viscosity is 290. Okay, for the calculation, we can do the interpolating polynomial using the Newton divided difference method. So the first divided differences, we got f naught 1 is negative 72, f11 negative 38, f21 we got negative 21. So the for the second divided differences, we got the f naught 2 is 1.7, f12 is 0.85, and for the last divided difference, which is the third one, is the f naught 3 is negative 0.02833. Okay, next, from the answer from the previous slide, we can make it into the table so we can see clearly, and we can put it into the formula below, which is the px f naught 0 plus f naught 1 multiple with x minus x naught plus f naught 2 multiple with x minus x naught multiple with x minus x1 plus f naught 3 multiple with x minus x naught multiple with x minus x1 multiple with x minus x2.
Now we want to estimate bitumen viscosity at 55 degrees using Newton divided difference. We plug to the numbers into this formula. Don't worry, we have done the math for you. After crunching the terms by step, we find that viscosity at 55 is approximately equal to 658.124. So, why does the matter outside the lab? It's because of performance prediction. Road face wheel temperature swings. Knowing viscosity at 55, a common intermediate temperature, help predict how pavement will hold up. Next was material optimization. We can choose bitumen that won't turn to soup in the heat or shatter in the cool, then compliance. Meeting design specs ensures safer, longer lasting road.
Hello, my name is Taiwei and I will present the discussion part. The primary objective of this analysis was to estimate the bitumen viscosity at 55 Celsius by using existing data ranging from 40 Celsius to 70 Celsius. The estimate viscosity value obtained was 658.124 Pascal second, which fall between the known value at 50 Celsius, which is 880 Pascal second, and 60 Celsius, which is 500 Pascal seconds. This confirms the reliability of our estimation. This finding is significant as it enhances our understanding of how temperature influence bitumen behavior, which is crucial in the context of pavement performance and material design. However, there is no limitation. The method used is more effective when the data points are smooth and evenly distributed. It is not suitable for extrapolation beyond the available data without further validation, as accuracy may be compromised. So we move to the conclusion. Understanding how bitumen viscosity changes with temperature is essential for effective pavement design and materialization. The use of Newton interpolation method provide a practical way to estimate value even without evenly spaced data, though accuracy still depend on the consistency and order of the data. This method is ideally applied to the interpolation rather than extrapolation, as external factors and noise in real-world data may reduce the reliability of estimate beyond the given range. The estimate viscosity at 55 Celsius provide valuable insight for making informed engineering decisions and minimizing the need for additional time-consuming testing in civil engineering projects. Thank you.